Welcome to week 10 workshop, CIV4SD3. Today we are talking about the two-way slabs, design of two-way slabs. We have started the examples in our lectures where we done the trial depth, and we also calculate the design bending moments. Yeah, today dress up a little bit differently today. I have an Engineer Australia course accreditation meeting straight after our workshop 11 o'clock. So therefore its dress up is about our course accreditation. Yeah, but I might finish at 5-10 minutes only, but it would not compromise your study or any details that we're going to skip it. Now before we go in the details of this workshop, I like to spend 5 minutes at least to just give a students in on this one. Let's move all these other stuff aside so no one interfere, and I have a calculator ready. Now what we have done so far, this one is not the correct one. Let's do this. So what we have done so far, I can remind you the problems. The problems that we have here is this problems is the two-way slabs. As you know, when your Ly over Lx is less than or equal to 2, generally you have these two-side bending problems. So that two-side bending problems, you need to provide the reinforcement in the x direction and reinforcement in the y directions, and these corner panels are the criticals. They will govern your design. So we need to design the corner panels in that case. I'm not going in the details again because we just like to move further. Now, as you know, we have to done the trial depth. The trial depth that we have selected is 170 millimeters. That's what we started, right? That was a lnx over 29, and there was like 170 is a reasonable number. As I mentioned, you should feel what is the depth of the slabs. You don't want to design something like these slabs, right? You agree with me? You need to have a physically visible, possible slabs. So 170 millimeters is a good starting point. Look, this slab is governed by the deflections. The designs is governed by deflections, serviceability. So there is a dim to comply ratio. This is very conservative approach. It's not accurate one, but at least it gives you the direction that 170 millimeters is accurate or not. And I discuss everything, how you calculate the effective length. This is the minimum depth meaning from the top of the slab to the Rio, how far that Rio is. That is your D minimum. K3 we discussed, K4 we discussed. This is given in example. EC we can get it from tables. FDEF we can get it from the equations as well. And we all done these done the calculations. And once we done the calculations, we found that we need the D minimum about 133, with the calculations give us 164, which is less than what we assume, which is good, right? This is the minimum 164 we needed. If we assume 160 millimeters, then you need to go back and redo all this one by increasing. So it's an iterative process. But 170 millimeters, the assumption is okay. Now further we assume that okay, look, 170 millimeters looks trick as well. For our economical purpose, let's drive 150 millimeter. Let's assume 150 millimeter. It's just optimization. It's just remove another 20 millimeters layer from that one. If it does not work, we can go back and increase the size. So let's start with 150 millimeters. And we talk, and then first steps is to calculate the moment demand. We call it design bending moment. At the mid span you have positive, because if you think that let's say you have this slab under this loading, let's say it is support here, under this loading it will bend, it will bend in that fashion, right? For that bendings you provide the positive reinforcement here. And if you think the bending moment diagram for this one would have negative bending moment, positive bending moments, and this one, so this is your positive bending moment. This is your positive bending moment, and this is your negative bending moment. That's what we need to calculate right now. So based on this positive bending moment, we provide the reinforcement here, tensile reinforcement, and we provide the tensile reinforcement on the top of the support. So these equations given in our clause, I can show you where that clause is. I think it's in the section 6. Clause 6.10.3.2, you have these two equations. Calculate the look, x is a short span, y is a long span. That's what it's mentioning. I think I already show it to you in the standards where they are sitting, and that is beta x fd lx square. Please note there is no typo in the standards. Someone might say you have y here, how come you put the lx here? This is governed by the shorter span, and I have a theory how you can prove that lx square. Okay, I discussed that one in the lecture. So you have two equations to calculate the positive design bending moment at mid span. So you can calculate the in the x, and right now we are working only in the x direction, shorter span. So then we have calculated this mx and beta x fd I already discussed, and we calculate this positive design bending moment in the mid span. Now someone might say that, okay, let me get my solution ready up so we don't screw up. All right, so now we want to calculate the this mx star is here. What is mx star? Where is the moment actually in the figures? So if you have, this is your x directions, because let's say this is lx and this is ly. If I take the 1 meter wide strip here, if I take the 1 meter wide strip across the x-axis, then if I draw that 1 meter wide strip, let's say this is a slab, and let's say this is the support, because this is the, let's say, beam here, and let's say this center to center distance is 5500 millimeters. I'm just drawing this 1 meter wide strip, and if I want to draw the bending moment diagram for this corner slab, I have this negative moment, positive moment, and negative moment, and this is your lx, this is your mx, this is your mx positive, right? So that is here, and we need to calculate the two negative, which is your mx negative, which is, so this is also mx star, and that is continuous continuous edge. So this is continuous edge. If you want to calculate the moment here, that is mx negative, and that would be also mx negative, that is also at the discontinuous edge. This is in the middle, mx positive. If you want to calculate the moment here, you have my negative, my negative, and you have my negative in the middle. So I hope you understand that all these mx and my. We will provide the bottom reinforcement in the middle. You have provide the top reinforcement at the support. So now we're going to calculate these two. Now let's so this positive bending moment we calculated. Let's calculate negative bending moment, which is the design bending moment. Negative design bending moment. Now the negative design bending moments that we're going to calculate, let's calculate at interior beam. Interior beams meaning at here. Interior beams meaning we're going to calculate here, right, for these corner panels. So now for interior beam, for this negative bending moment, we're going to use this clause. Okay, now we're going to use this clause, say that negative design bending moment at continuous edge. Clause 6.10.3.2b, we have 1.33 times of mean span value of direction considered when they are taken from this A. Right, so table A, yes, we use table number A, that's good, beta x. and we're going to multiply your mx value with 1.33. So mx negative, let's say star, is your 1.33 times by mx positive, and that is at the midspan one. Okay, that is the given in the close close number 6.10.32 b. Right, so 1.33 times by 14, that gives me 1.33 times by 14 gives me 18.6 kilonewton meters, and we will get the negative bending moment. We're going to get the negative bending moment. If you turn the page over, you have a negative bending moment. If you turn the page over, then you have C, negative design bending moment at this continuous edge. You have 0.5 times at midspan value of direction, this one midspan value in different directions when you use these tables, but we are using this table, so we have 0.5. Using these tables we have 0.5. So at this continuous edge, what does this continuous edge meaning? That negative moment, because you have two options. One is at continuous edge. This is your negative moment. This is your continuous edge. This is your continuous edge, and this is your discontinuous edge. This continuous edge, the moment here would be 1.33 m positive. Moment here would be 0.5 m positive, and m positive you can calculate here, right? So that's what written here in the close. And let's go back and put that details there. That negative at the discontinuous edge, mx negative equal to, let's say, mx negative star 0.5 mx positive, and this is midspan 1. So it is just a 0.5 times 14, you get 7 kilonewton meter. So now we calculate all the required what we call all the required design bending moments. And now the procedures are same like a one-way slab. There is not much difference now between the two-way slab and one-way slab. If you follow the one-way slab, then these procedures would be quite simple. Now, so we have all the three, and in case someone wants you to design, so don't hesitate and don't worry. We are currently designing these panels, right? We are currently designing these panels. If someone asks you to design these panels, that's fine. You can calculate the moment here, cantilever moment here, because this is continuous. So it would be 1.33 m star, 1.33 m star. That m positive here, that is m negative here, and this one here, this continuous. So this is x and y. I can show you y how to calculate. If someone ask you this one, you follow this procedure. Someone asks you this one, still again you are in the positions to calculate this positive. Any panels that you going to do it, you will be able to calculate. Okay, don't hesitate saying that okay, I can only do the corner panel. No, you can do any panels, right? Because I'm explaining you everything. It's continuous edge, discontinuous edge. Generally you need the moment, design bending moment, design bending moments here, 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 design bending moment here, design bending moment here. And let me put this red one. Red one is a negative, black one is positive. Red one is positive, red one is negative, and black one is positive. So you are in the positions everywhere that you can calculate. If someone tell you, can you please give me the moment here? Now you are in the positions that you can calculate the moment in anywhere in the slab. Once you know if there is a positive or negative, once you know your moments, you can calculate the Rio. Unmute yourself if you tell me that, okay, I don't understand this particular panel, how do you calculate? I think all good, no one talking. So we have these positive bending moment, negative bending moments. So we have three bending moments. Positive bending moment, positive bending moment 14 kilonewton meters at mid span. MX negative at support, which is how much was it? 18.6 kilonewton at the support, but at continuous edge. At support at continuous edge. And we have another negative, which is 7 kilonewton meters, which is at support again, and that would be your discontinuous edge. Right, I hope you understand that. Now based on this one, we can easily calculate what we need to what we need to do, the reinforcement. I think you follow this example with me. So let's calculate the positive, this first one. Let's calculate this first one. Let's calculate the bottom reinforcement at mid span. This is due to positive moment M positive equal to 14 kilonewton meters. Now once you know the moments, I think what we are doing here, that let's say I draw the corner pylon here and I'm going to direct a 1 meter wide strip. So that is act as a beam. What is the beam meaning? That okay, this is like a kind of a beam, which is, let's say this is 5.5 meter beam, and let's say support is here, and this is 5.5 meters. And so instead of slab, this whole slab, what we are doing, we are just taking this 1 meter wide strip in the slab, and then once you find the reinforcement in the 1 meter, we will just distribute that 1 meters along these 7.5 meters, right? So once you know the reinforcement in 1 meters, you can use the same distributions over the 7.5 meters. I hope it makes sense. So in the beam theory, we know that if you have a beam, which is 1000 millimeter wide, that's what we assume, which has a 150 millimeter slab depth, is a beam depth. So, and then we are using N12 Rio, but we don't know how many Rio that we going to calculate. Then you can calculate this D. I think we already calculated that D, but let's calculate here again. That small d equal to 150 millimeter. Take away 12 divided by 2 millimeter. Take away, I think 25 millimeters is a cover. So 150 take away 6, take away 25, you get 119 millimeters. That is the depth. So as you know, in the beam examples, when you have this 100 and sorry, this is 150. This one is 1000. This one is 119. And if you remember this diagram, I just draw the force diagram. This is the force in the concrete, this is the force in the Rio, and that is your lever arm Z, and that is your moment, right? So if I want to calculate the moment would be tensile force times by Z, right? That is the lever arm. And we have to make an assumption here to make it Ku equal to 0.36 ductile. We said that lever arm would be 0.90. This is the assumption, and this assumption works for every beams that you want to design for ductility. So we assume this one, and nothing wrong in these assumptions, right? This is a very conservative assumptions. It's always work in the slab. We don't want to do the example again. You find a neutral axis depth, you find this all these strain, whether the top bottom Rio is in the yielding or not yielding, and then you find this beta 2, this alpha 2, gamma, and so of course there is nothing wrong in that one. In the real world, or in the and when you are graduated and you are sitting in the office, you can do that. There is no any issue. I'm not stopping you that you don't want to do it, and that is the correct way to do it. You might get the conservative answer, but look, this AST that we're going to calculate, that would be approximate. It is not correct, because you're going to check your minimum reinforcement, you're going to check the shrinkage and so this 0.9D is going to save your time, save your calculations time. Of course, when you want to optimize, and again, there is a second assumption as well, that this slab design does not govern by bending, does not govern by the strength of the bending. We don't say that, okay, depth of the slab is 150 millimeters because its bending strength is more than the design bending moment, and we said, okay, deflection is okay. No, this slab is generally governed by the deflection, the serviceability. Therefore, we don't focus too much on the bending. Bending, we're going to do it just to calculate the RIO, right? So in that case, is a let's say you know this story that 5mu should be greater than your m star. You know this one, right? That capacity of your slab or 1 meter wide stream should be greater than your demand. For mathematical purpose, let's just remove that greater than, just put nothing wrong to put keep greater than this. Okay, let's keep it greater than this 1.9 0.9 or 0.85, I believe 0.85. If you go to the capacity factor table, here you go, I think 0.85 bending, 0.85, that we, because we have ductility here, Ku is satisfied, so we are using 0.85. So 5 is 0.85, mu is your tension force times the Z, greater than m star for mid span. M star mid span 14 kilonewtons meters. So you have 14 times 1000 times 1000 to use it in Newton millimeters. Now 0.85 tension force is AST of the steel tube, and FSY tension will, because when you take this 0.9D, I'm sure this steel will be yielded for sure. That is 100% sure. And 0.9D, that is your Z, greater than or equal to 14 times 1000 times 1000. So let's substitute FSY for N bar. For N bar, FSY is 500 megapascals, Newton per millimeter square, 0.9. The D we just calculated is 119 millimeters, greater than or equal to 14 times 1000 times 1000 Newton millimeters. So everything looks good. So AST greater than or equal to 14,000 times by 1000, that is Newton into millimeters, over 500 Newton per millimeter square, which is megapascals, 0.9 times 119 millimeters. So if I calculate this one, 14 times 1000 times 1000 divided by 500 times 0.9 times by 119, you get 261 millimeter square per meter. Please note this is per meter, right? It's not over the slab. It's just every meters you will provide 261 millimeter square per meter. Now that sounds good. Let's do exactly the same thing for this one, that we have another one, right? This one, continuous support, only 18.6. So let's do the second one, negative or top RIO. You said top RIO reinforcement at continuous edge or support, that is due to negative bending moment. negative bending moment was continuous edge 18.6 kilonewton meter. 18.6 kilonewton meters. Now in here, that would be everything same except this 14, because that's what we're going to change it. So AST greater than or equal to, instead of 14, I'm going to use 18.6, because everything is same, right? There is nothing change. Same Rio we're going to use, N12.9, same Z, same D. So in that case, I can just calculate that. 18.6 times by 1000 times by 1000 divided by 500 times by 0.9 times 119. You get 347 millimeters square per meter. And the last one meaning this is top Rio. Again, top reinforcement, because negative you provide the top tensile reinforcement. Top tensile reinforcement at discontinuous edge. Discontinuous edge, I'm talking about discontinuous. We just calculated the one here, and we just calculated here continuous edge. Now we are calculating at discontinuous edge, top Rio, and that has a negative moment 7 kilonewton meters. I can show you to, I can reference that one, that discontinuous edge we have 7 kilonewton meters. So for that, so that is due to 7 kilonewton meter M negative. Let's say start. So everything is same. AST greater than or equal to 0. 18.6 replaced by the 7. 7 times 1000 times 1000 over this 500 megapascals times by 0.9 times by 119 millimeter. So AST greater than, let's use my calculator. If you don't understand anything, just tell me, okay? 131 millimeters square per meter. So now we found three different reinforcement. Let me check. 326 was right. What is that? Let me check what is happening here. 14 times 1000 times 1000 divided by 500 times 0.9 times, oh, I forget, sorry, this one 500.9119, I forget this 0.85. Sorry, please make a corrections. I just need to recalculate this. Divided by 500 times 0.9. Yeah, I suspected that these numbers are just not appearing. 307, 308, that sounds good. 308 millimeters square per meter. Again here, just multiply 0.85, that capacity factor, I forget that. Let's recalculate that. Divided by 500 times 0.9 times by 119 times by 0.85, you get 409. 409 millimeters square per meter. That sounds good. And then you have this, just multiply by 0.85 here. So 7 times 1000 times 1000 divided by 500 times 0.9 times 119 times 0.85, you get 154. So that sounds good. Now we found these three reinforcement, right? We found these three different reinforcement. If I redraw this reinforcement, let's say in the slab, this is your beam, this is your slab, and this is your continuous. So we found this reinforcement here. That was bottom reinforcement due to positive bending moment. How much we calculated was 308. Was here we have AST of 308 millimeters square per meter. And by the way, this is distance 5500 millimeters, right? I'm just drawing this. When you look at from this end, I'm just drawing these slabs. So when you look from here, I'm drawing elevations, okay? And I draw this beam, and I draw the slab. And the slab thickness was 150. Let me put that one, so it will make more sense. So you have these 150 slab thickness that we are working right now, and then you have this top corner view. That is continuous one, 409. Sorry, continuous one is top one, 409 millimeters square per meter, and at the discontinuous edge you have 154 millimeters square per meter. So that was the based on our bending moment. You remember we have a bending moments here. Positive bending moment was 14 kilonewton meters. Here we have a 18.6 kilonewton meters, and here we have a 7 kilonewton meters, right? So that is the bending moments that we obtain AST from that bending moment. Now there are a couple of checks that we need to do it. The first checks that we're going to make, there is a couple of checks that making sure that these numbers 308, 409 and 154, there are three AST at let me list them. AST at the mid span we have 308 millimeters square per meter. AST at continuous edge we have 409 millimeters square per meter, and AST at discontinuous edge we got 154 millimeters square. Now we're making sure that these ASTs, three ASTs, AST number 1, AST number 2, regardless of their position, whether positive or negative, we make sure that this AST is greater than minimum AST requirement, right? This AST, there are three, 1, 2 and 3, one at the mid span, one at the continuous edge, one, and regardless of their positions, wherever you're going to put it, you should provide the minimum reinforcement. This is to some engineers might end up not providing any reinforcement and in particular sections. Why? Because they might say that, okay, my bending moment is not that significant, so I don't need Rio. Now the standards, if you have a concrete only and you don't provide the Rio, is very dangerous. Concrete is very brittle materials. It will just snap, break, and whole structures will come down. So we don't want to do it, those kind of things. I think recently we have this Melbourne earthquake, about 6 magnitude, that earthquake that we have experienced. So structural engineers are on the call for this kind of disasters, where our design will be tested when you have this earthquake or some other disasters come. So you during that earthquake, if you have a concrete only, your structures will come down straight away without warning. We don't want to happen that one. If the structures fail, we don't worry about it. If structures bend, we don't worry about it. If structures crack, we don't worry about it. But if structures come down and some life is lost, that's the worry part for us. We don't want to happen that one. Okay, so in that case, the standards telling us, you remember that in the one-way slabs we use this one. In the one-way slab we use this one. We use this one, AST minimum close. When you come in the beam one-way slab, that is governed by AST 0.2 D square FC to depth FSY BW and D. So that is 0.9, so 0.2 here. Now for two-way slab, standard is little bit same equations, almost same, but standard has just reduced these AST minimum, that you just need to because you know these are are stronger slabs, so they are just require less reinforcement in the two-way slab, just slightly less. So you're going to use these bending, because I think they mentioned somewhere here that slab supported by beam and walls on the 4 sides, right? You can see, so you can't use this one on the one-way slabs, or this one also you can use it when you supported by the columns at the corner. But here we're going to use this one, not this one, because our slab is supported by 4 sides. Now this AST minimum, this is to prevent the structures from the brittle failure. Your structures will not come down. So regardless of your design, regardless of your moment, regardless of your cover, regardless of your span, whatever you do, plus minus multiplication division, you making sure that your AST that you have calculated should be more than this one. No questions to be asked, and I don't want to compromise this one. You must have this minimum RIO in your design. If you argue with that one that okay, my moment is too low, I don't need any RIO, no, there is no any argument here. Straight away, very hard line, that 0.19 you need to have that AST minimum in your one. So let's calculate that AST minimum that to prevent from brittle failure, from that sudden snap failure, and FCT FCT.F dash over FSY. Now that is coming from the clause 9.1.1. Now FCT.F, which is the characteristic FCT.F dash, that is coming from here. FCT.F here clause 3.1.13 FCT.F, which is the characteristic flexure tensile strength, which is 0.6 times square root FC dash, which is 0.6 times square root FC dash, and that is coming from clause 3.1.13, which gives me 0.6 FC dash. We have given in our examples. Let's get that details. You have FC dash 32 megapascals that we're going to use. Square root 32. So you have a 0.6 times square root 32, 3.4 megapascals. FSY is 500. FSY is 500 megapascals because we are using N bars. Capital D is 150, which is the slab thickness, and N12 bars we have calculated this 119, which is your small d. This is capital D, and I think I pointed out where is the small d. We calculate that here. Small d 119, that is just from top of the slab to the RIO. So let's calculate this AST minimum. AST minimum equal to 0.19 times depth of the slab is 150 millimeters over that effective depth is 119 small d. FCT depth 3.4 megapascals divided by FSY 500 megapascals. So in that case, you can just plug that values in your calculator and get the AST minimum. 3.4 divided by 500. You get, I think I done something wrong there. I did not do the square here, sorry. So there is a square there, okay, yep. So 150 divided by 119 square times 3.4 divided by 500 times by 0.19. I'm not 150 divided by 119 square times by 0.19 times by 3.4 divided by 500. What is happening? Oh, okay. Just give me a minute. Okay, so Yeah, I just need to clarify that one. Yeah, because you see, uh, uh, let me clarify some of the points. You see this one here, they have multiplied B and D. So basically this one like a AST on BD, like a reinforcement ratio AST B on D. So they have give you here, this is a reinforcement ratio. They mentions that one, tensile reinforcement. So AST BD, see that's one they written AST BD. So we need to take AST BD. So that was my just little correction here, that let me write it again. AST minimum on BD should be greater than or equal to, because it's not less than 0.19, 150 over 119 square over 3.4 over 500. Now that makes more sense. AST minimum over this B is 1000 millimeters and depth is 119 millimeters, greater than or equal to greater than or equal to 0.19, 150 over 119 square over 3.4 over 500. So AST minimum would be 0.19, 150 over 119 square times by 3.4 over 500 times this 1000 millimeters times 119 millimeters. Now that is more sense. AST minimum would be 115 over 119 square times 3.4 divided by 500, 19 times 1000 times by 119. So that makes more sense. Still, what is happening with me today? 150 over 119 square times 0.19 times 3.4 divided by 500 times by 1000 times by 119. Yeah, 244. That sounds good. Millimeters square per meter. So regardless of your calculations, this 3 should be greater than 244 millimeters square. So let's check. 200 AST minimum equal to 244 millimeters square per meter. So this is good. Let's put this on green. This is good because your AST 308 millimeters square per meter is greater than AST minimum, which is 244 millimeters square per meter. So that is good. 409 is good because you have 409 millimeters square per meter is greater than 244. That is good. Now this is not good. You can look at that 154. That nothing good means we don't need to go back and change it. Meaning just we need to change this one to 244 millimeters square per meter. That's we just provide the minimum here. So here we just going to change this value to 44 millimeters square per meter. Right. So our after minimum we have again three values. AST at the midspan, which is 308 millimeters square per meter. Your AST at the continuous edge 409 millimeters square per meter, and AST at the discontinuous edge we just provide the minimum that is required. So it is at the midspan, bottom Rio, top Rio at continuous edge, and this is at discontinuous edge. So if I redraw that slab again for your reference, this is your beam. This is your 150 millimeter thick slab, and you are providing this x directions Rio, which is AST at the midspan, positive bottom Rio, 308 millimeters square per meter. You are providing this top Rio, that is AST of 409 millimeters square per meter, and here we change it to satisfy that condition, which is 244 millimeters square per meter. That is the AST top Rio. Right. So I hope you understand that this is your midspan. This is your midspan governed by positive bending moment. This is your continuous edge that is governed by negative bending moment, and that is your discontinuous edge. this continuous edge. Now we done so far. Our beam will not going to collapse regardless of our conditions. Our beam will not going to collapse. So this is the, when you provide this reinforcement, your slab will not going to be collapsed. Now there is a one more conditions though that we need to follow. There is a one more conditions, meaning look, this slab are thin and wide. They are spread across on the both sides. Now in that case we need to make sure that will not gonna crack. So first checks we done, that is minimum reinforcement check, that we done right just now, and that is to make sure reinforcement check AST should be greater than AST minimum regardless of that one. And the second check for that one we're going to make is called shrinkage and temperature crack control check. What does it check mean? That your slab will going to shrink over the time, right? And it will goes to the various temperature cycles over the life of your slab. So in that case standards does not want to see the crack happening on this one. In the beams generally this crack is prevented by providing the spacing, but in here we have these specific sections given particularly for the crack control, for shrinkage and temperature for the slab. Now let's do these crack controls. So we have a 9.5 point. So X is the primary. Look, this what does primary and secondary meaning? That you have this slab, which is 5.5 meters in these directions and 7.5 meters in this direction, right? That is given in our examples, right? That's corner one. Look, this exercise can be followed and you can think of for any panels. Okay, so here you have this one, so 5.5 meters and 7.5 meters. That's what I draw that. So if you have that one, and thickness is 150 millimeters, let me put the thickness as well. So I'm just pointing it out, primary and secondary one. So you have this thickness of the slab is 150 millimeters. So in that case, this is your X directions because shorter span. This is your Y directions. So this is your primary direction, by the way. Primary directions. Why this is primary directions? Because when this beam going to bend, when this beam bend in X and bend in the Y directions, it will going to bend. So the X direction will carry the more load, right? That's X direction, you can see that one. So we need to provide the primary reinforcement which will significantly carry the load. So you, let's say at the mid span, you provide this bottom reo. I hope in the 3D you can see that. So that is the bottom reo in the slab along the X directions. And again, you also provide this top reo at the discontinuous edge. Let's say here discontinuous edge, and this continuous edge at top reo you provide this continuous edge top reo, right? So this is your primary reo. This is your primary reinforcement. Now in the Y directions, in the other parts, then you will going to provide these Y direction. And similarly, you have this top one in the Y directions as well, and in the top one continuous one Y direction. It's like a mesh. You can say that mesh of the reo. So you can have these in the X directions, and then you have these in the Y directions, right? And the X direction we provide this one bottom reo in, like if I draw the cross sections here, 150. So this is my primary, and then secondary you provide on top of it, right? So that is how. So this one is a primary, and let's say this is X directions, the shorter one, and this one is secondary. Secondary we have not started yet, but I will show you secondary one in a minute. So primary one we are working on. I'm just come across that word, so I explain you what is primary and secondary. So because in the standards they are using that wording, that say reinforcement in primary directions and reinforcement in the secondary direction and so on. So don't get too much worry about what is the primary and what is the secondary. So we are working on primary one 9.5.3 because we are working on x direction. Do you remember we calculate mx only, mx positive, mx negative, and so on. So in that case they said that reinforcement in the primary you need to provide the 75% of the area required by one of these close. So you need to come onto this one, which is secondary close 9.5.33 on Rusten slab and partial Rusten. There are three close that different clauses are given. Now generally we have a Rusten slab. This one, does it given in the question? If not given, we can generally assume that is a Rusten is sitting on the slabs. It's not like a free to expand, right? It has a beam connected and all column supports and so on. So that is Rusten slab. If you don't know, then you can put the assume, you can assume that. And let's say this slab is sitting under in the closed environment, like these classifications, like classification even depending on where the slabs are sitting. So let's say moderate degree of control. We don't want to go for minor one. Let's do the middle one, moderate degree of control. So we make two assumptions. First assumption saying that okay, restraint slabs, and then you have moderate degree of control. So in that case you can just take these equations as an AST minimum for the crack control. And by the way, don't forget to multiply 75% because they want to multiply 75% with this one when you're designing it for primary direction. For secondary direction you no need to multiply it, because in the secondary direction we generally provide temperature and sinkage one in the secondary directions. Those blue ones that I just put it here, this blue one is not contributing too much in the moment side of it. Of course in the two-way direction they do, but they more towards the shrinkage and temperature too. I will show it to you in the one-way slab. If you remember, we don't do any moment check on this one, but in the two-way slabs we do. But they generally have a more purpose of serving for shrinkage and creep. Shrinkage and temperature. So we okay. All right. So for the shrinkage, we have a AST minimum should be greater than 75% of 3.5 take away 2.5 sigma CP BD times 10 raised to minus 3. Now in that case we have this close which is 9.5. We just use this 9 close 9.5.3.2. let's put that close close 9.5.3.2. all right. Now sigma CP, the story of sigma CP is if you come back here, sigma CP alphabetical order, sigma CP average intensity of effective pre-stress in the concrete. We don't do the pre-stress here. So pre-stress is not allowed. Pre-stress we not cover in this course. So sigma CP is 0. So AST minimum is 75%. You can just divide by 100. 3.5 minus 0. B is 1000. Def is 150 times by 10 raised to minus 3. So AST minimum. Let's plug that one. 75 divided by 100 times by 3.5 times by 1000 millimeter times by 150 millimeters divided by 1000. So you get 394 millimeter square per meter. Now this 394 millimeter square per meter. Let's check again. Remember 393. AST minimum is 393. Let's see who gonna pass. Who gonna pass meaning that who going to survive. This guy is not going to survive because we need to change this one because it's less than that one. If you don't change it, then your beam will crack at the mid span. So to stop that cracking, we need to provide 393 millimeter square. This one good because 409 is greater than 393. This one no good again. We need to change it. AST is equal to 393 millimeter square per meter. So when you change 393 again, it's still satisfying this one, right? Again, it's still satisfying this 244. So that is good. Again, this one's 393 satisfying 244. That is good. And this 409 still satisfying 244. So that's, make sure that when you reduce it, I think that the way we follow, I think when you do the if you do this crack and this one, that you might compromise this one. So therefore we do this one first, because this is always lower, and then we follow this creep and shrinkage. So you will not be, what can I say, it will not be affected in our design. So let's do the revision. The revision meaning that we have a final some kind of values, that you have 150 millimeter depth. We have a bottom reo, which is, oh sorry, we have a bottom reo that is what is, how much, 393, because we change it, I believe, millimeter square per meter, right? Yes, we change it. 409, we did not change this one because that is greater than this one. So here you have a 409 409 millimeter square per meter, and we have this one again we change it, 393 millimeter square per meter. So I hope you understand so far that we done the two checks, that we check that will satisfy those conditions. Now we need to find the spacing. There is an equations, by the way, to calculate the spacing. If in case you want to calculate by spacing, if you remember one of my video or one of my one-way slab one. So let's say you know the area, that spacing you need to calculate one from that another one. You know this is thousands, right? Because we assume that is 1 meter wide strip, and N12 bars we are using. So we are interested in calculate the S. Now what is the area of 1 bar N12? Let's get that one in here from the Rio table. Come on. Okay, N12 bars, 1 bar, you have a N12 bar, 1 bar, you have 113 millimeter square. So area of bar, 1 bar, N12 bar is 113 millimeter square. Let's say total, let's we want to calculate here 393. So area at the midspan is 393 millimeter square. So easy here, we can take the ratio. So let's say spacing of the 1 bar, spacing from the 1 bar, area of the 1 bar 113, total spacing total space is 1000 millimeters over the total area is 393 millimeters square. Just take a ratio. So the spacing that we want to calculate, 1000 millimeters times 113 millimeters square over 393 millimeters square, you will get 1000 times 113 over 393, you get 288 millimeters. Generally we don't make it 288, we round it off to the nearest, because your builder will not, you're not going to go and just measure 288. They generally like to have a rounding number. This is the mathematics, but we straight away use these tables. In the next page, if you have a, what we look at, they have give you the Rio tables, give you that spacing as well. So here what we do, we just going to check 393 number and come back here. On here we have a N12 bar, 393, 377. We can't use it 370 because we need to find the area which is more than 393. So you have this 411. Okay, so that is works, and we provide 275. So that is good. That from Rio tables, if you have a 393 millimeter square per meter as a calculated area, we can provide N12 bar at the rate 275 millimeters, and AST actual meaning from the table is 411 millimeter square per meter. So if you take 400 millimeter, still it satisfy the shrinkage one 394, and it still satisfy these 244. Therefore in the tables I suggest you to go for more than the value. So 411 275. So that's kind of first one. So what we do, let's redraw this figure again. Let's redraw these figures again, and let's provide these Here we have a N12 bar at the rate 275 millimeter of the bars. Okay, let's do this one. N12 bar. You can again use these equations like 113 over what was that here, 409. You can just put the 409, but I just going to straight away use here 409. So I think 411 still okay, and 275 we can use it. So here we have a N12 bar and 275, and for that one, actual one, let me write that one, N12 at the rate 275, AST actual is 411 millimeter square per meter. That is at the continuous edge. This is at the mid span. This one as a mid span. So I'm also writing that reinforcement as well. Here you have a N12 at the rate. How much we needed? 393. Again 393. Again 393. This will not work. 411. So 275. And it looks uniform. You know, your builder will not going to like it. You have 280, 270. They will order the mesh with this standard mesh. So from that Rio tables, you can just put this N12 275 everywhere. So we have a N12 at the rate 275 everywhere in the corner panels, and all AST is 411 millimeter square per meter, which is greater than your AST minimum, and for the ductility, and is also greater than your AST minimum of temperature and shrinkage. Right, so that is all good. I think this is the finish of the primary. This is the end of primary reinforcement. Primary reinforcement at corner panel. At corner panels. If someone asks you, can you please do the calculations for this one? Yes, you can do it. There is no any issue. Someone will ask you, now with this exercise, you are in the positions to calculate the reinforcement anywhere in the slab. Okay, anywhere in the slab, you are in the positions to calculate. The first thing first, you can have a trial depth. Let's say any depth. You have a trial depth. From this trial depth, you can just do the deemed to comply, and once it's deemed to comply, you calculate this positive M star at mid span or continuous, discontinuous edge, M negative. From this negative, you can calculate AST. You can do the two minimum reinforcement check for ductility, and you do the temperature and shrinkage check, and then one more check I forgot. Then you do calculate the spacing. Now there was one more check. Sorry, I think it comes in my mind now that we need to do the spacing as well. The spacing that we provided, it should be okay, but we need to do the spacing check, that minimum spacing check. Let's finish that one here. So that's fine. Let's not finish here. Now we will have a minimum spacing check. Again, this is for the crack control. And someone might say, Vipul, what are you talking about this crack control? Because you already checked the shrinkage and temperature. Look, this minimum spacing is the fluxure crack control. So when the slab will going to be loaded, when the slab is going to have a dead load and live load, making sure that due to that dead load and live load, you will not allowing the crack to be generated due to the loading. So to stop that to stop the cracking, the fluxure cracking, or this, those fluxure cracking, that would not affect you need to stop that cracking due to the loading. Now for that one, the standards helping us. I think I need to find that close spacing one. I think the close one is 9.51B. Let me find that one. Oh, here you go. Crack control of the slab, general requirement. I'm just going on this one. unless cracking beam to control by the pre-stress. We don't have pre-stress. We need to provide the minimum spacing of 2 ds and or 300. So they said that minimum spacing equal to minimum of 2 ds or 300 millimeters. Now someone might say, what is ds? If you go back to the start of your standards, and they will give you capital D. Where is the capital D? Okay, D. They did not mention, so yeah, ds, overall depth of the slab. So that is good. Our overall depth is 150 millimeters. So minimum of 2 times 150 times 300 millimeters. So you have between that is 300 millimeters. So all the spacing which we have is 275 millimeters. Our actual spacing is 275 millimeters, which is less than your S limit or minimum. The standards wants to provide 300 millimeters everywhere. Again, this is a space, this is independent of your space or independent of location. I mean, independent of locations. Everywhere you need to have a 300 millimeters. So where you design the slab, or if you go to the supervising side, you will never the look, this is American one, we follow American one as well. 300 millimeters meaning 1 foot. Your Rio, first Rio to the second Rio, this is the distance that you need to have, regardless of your design. Someone will not be able to, if you tell that I put the 400 millimeter Rio, completely wrong. They said I don't design. No, there is no way you will have a 400 millimeter spacing of the bar in the slab. There is no way. Why? Because you can look at that 300. If you have a 160 millimeter, that become 320. They will prevent you this one. So there is no way, there is no design in the slab that will telling you put the bar 400 millimeters apart. If you put your bar 400 millimeters apart, the beam will going to, a slab will going to bend, the crack will going to appear. So that, to stop that one, you need to have this one. So you can see that just like a one hand, right? If you don't have ruler, you can go and just put that your one hand 1 foot like that. I'm just talking about this from this end to this hand. So when you go on site and when you see the slab, that is this one, it's not. And our Rio tables also follow that. Rio tables also follow that. Look here. They will not supply any reinforcement spacing more than 300. They generally supply like this. They will supply this meshing like 200. They will, you say that, oh, hello Rio, I want 500 plus rebars. I want the spacing of 400. They will tell we don't supply 400. Full stop. Why you don't supply? They will not tell you why, but there is a reason for it. There is a reason for it. This guy is stopping them to produce more than 300 millimeters in the factory. In the this one, they never produce more than 300 millimeters, because if someone produce more than 300 millimeters, no one going to buy it, because no one going to buy it, because who gonna go against the standards? If something goes wrong, we are in the trouble. So I hope you understand that you have 275, 300 millimeters is a hard line, that you never ever design the Rio which is more than 300 millimeters. All right, so I think this is the end of the primary Rio. It's a long one, but I hope it is worth it with the time. You can stop me if I run quickly. So let's say let's say design of reinforcement. While I'm writing, if you have any question, just unmute and tell me. In the secondary Y directions, I already explained what is secondary Y direction and its long span, right? If I quickly draw the figures, that slab is 150 millimeter and you have this slab 5.5 meters. This is your primary direction, this is your secondary direction. So this is your primary and that's blue one is the secondary. So now we are designing, we done primary, now we done the red one, now we are going for a blue one. So there is a one good one here, like if you remember that in my examples that you have N12 bars and we calculated this 119 from 150 millimeters, right, Dave? Because you have 150, take away 12, divide by 2, take away 25 millimeter cover, you have 119. Now for the secondary one, that will going to sit on top of the primary one. So let's you have this primary one and there is a secondary one on top of it. So in that case, we need to calculate the D again. By the way, this is your dx. Okay, if you want dx equal to 119. Now dy is equal to your 119 already, and take away these another 6 millimeters. Right? I hope you understand that. 119 take away 6, you get 113 millimeters. Right? I hope you understand that, because if I magnify that one, that you have this Rio, and someone asks you to calculate, let's say this is a secondary one, and this is again N12 bars. Someone wants to ask you to calculate this dy. So in that case, you have this 150, take away this cover 25, take away this 12 millimeters, take away this 12 on 6. I think this one wrong. Let's check it out. So 150, take away 25, take away 12, take away, oh, this is divided by 2, sorry, take away 6. Oh, this is 107, because I should take away 12. So 107 is a dy. I hope you understand that. So in the calculation in the y directions, we will going to take a dy equal to 107. Now again, we're going to calculate the three different values, with three different moments. So here in this close my, you have beta y, fd, ln x. That is the equations that we're going to use, positive. And by the way, this is positive at the midspan, positive design bending moments at the midspan, right? So let's do that. My plus my star, let's say plus my star is equal to beta y fd. Remember this Lx square, right? It's not Ly, by the way. So beta y, beta y is here, long span coefficient beta y. We are working on the 2H discontinuous 0.035. That is your beta y. And it's independent of Ly on Lx, right? Beta y is 0.035. So let's put that one, 0.035 times by fd. We calculate fd before. It's not going to change the loading in the x direction or y directions. If someone walking, it will not showing to say that I'm walking only in the x direction. So 9.6 your dead load and live load, so that is stay same. So that would be your 9.6. Lx we already have 5.15 square. I'm just following this one. We already calculate mx. We just going to change few things. That you have, where is the mx? Yeah, positive mx. You have these factors going to change. 9.68, this will stay as it is. So it's just 0.055 change to 0.035. So in that case, let me find it out, that one. Look, the procedures would be exactly the same, just some factors would be different. 0.035, 9.6 times by 5.15 square. So 8.9. Look, remember there was a 14 kilonewton meters in that x direction. So negative my star at, let's say, at the, again follow the same thing, at the continuous edge you have 1.33 when you use this table A. So you have a 1.33 negative, we don't put negative, just keep in mind that is negative, times by 8.9. So 1.3 times 8.9, and by the way, this is continuous edge. I'm not writing everything here, so that is 12 kilonewton meters. And negative my star at the discontinuous edge, at the this continuous edge. I think this is just a repetition, 0.5. I think you know the story now, that 0.5 times 0.89, you get, oh sorry, 8.9 times 0.5, you get 4.4 4.5 kilonewton meters. Once you know the moments, you can calculate AST. AST equal to, one time you put this 8.9 should be greater than 8.9 times 1000 times 1000 over 0.85. Don't forget that one. You remember, I forget that. And 0.9D here is 107. Where this coming from? You remember that one, right? We done 3 times this one. This one. Same equations here. Where is it? Here. 18.6, 500.9, 115. There are 4 here. So I'll just change this one to whatever the value we have, right? We done that one. For primary directions, we're just changing the moment. So in that case, we will get 8.9 times 1000 times 1000 divided by 0.85. 0.85 times by 500 times by 0.9 times by 107. So you get 217. Let me check whether I'm going in the right direction. 217. I think that should be okay. So you have 217 millimeters square per meter. Similarly, we use this 8.9. Instead of that, we use 12. We use that one. So in that case, 1200, 1000, 12.85 times by 500 times by 0.9 times 107. You get 293. This is at continuous edge. And AST, again, instead of 12, we're going to use 4.5. 4.5, I'm not writing it, divided by 0.85 times by 500 times by 0.9 times by 107. So you have about 110 millimeters square per meter. Now all these need to be checked. Check meaning you remember that our beam should not, our slab should not be collapsed, and there was minimum one. What was that, please? This is 244, and again this is independent. Someone said you need to recalculate. No, if you recalculate, still it will give you the same answers. Okay, so you remember this close, that 0.19, and we calculate this 244. So make sure everything is greater than 244. I explained you that one, right? 244 millimeters square per meter. So is it okay here? No, this is wrong, because we need 244 millimeters square per meter. This is okay. This is wrong. 244 millimeters square per meter. So that is first check is okay. Now let's redo it again. AST is 244 millimeters square per meter at midspan. AST at the continuous edge 293 millimeters square per meter. They done the one check done. AST greater than or equal to 244. I hope you following me. Second check, that's shrinkage and temperature. We need to stop the crack due to the shrinkage and temperature. What was that value, please? I think that was 394. Is it? Yep. No, but here we need to recalculate that one, because I think it's in the secondary direction. So now we need to recalculate this AST minimum here as well. Look, I need to. I will go through that one. Through that one, okay? Because I think I missed the values there, because we need to recalculate that AST minimum again, because your dy is different, so we can't use this one. Let me now share with you this one through the, because it's we will not going to be finished if I keep you now. Is everything I put the close in front of you? All right, now I think what we finished so far is I think we done this. I think we done this deflection check I will tell you later. Yes, so secondary directions we are talking about. Now in secondary directions, I think we calculate these the reinforcement. We calculate the reinforcement at the discontinuous edge, continuous edge, and we calculate those three reinforcement, right? And based on three different moments. Right, now we need to recalculate this minimum reinforcement. Why? Because your D is different. You remember that you have 107, right? If you remember that one, that in before in the examples we are using 119, right? We use 119. Now here our small d value changed to 11107. So in that case we need to recalculate this ESD minimum. Quite easy, exactly the same things. There is nothing changed except this 107, and then you have a 272 millimeter square. Now all these value that we have calculated, 230, 305 and 116, they need to survive for this 272. Survive meaning they should not be less than 272. So 230 230 first one not okay because it's less than 272. So change it to this one, change it to 272. So I change it. Interior beams 305, that is okay because greater than 272. Discontinuous edge 116 not okay. Let's change it to 272. So not okay doesn't matter. We just change this. We just change what we calculated here. 272. So we just change this one to 272. This one okay. We change this one to 272. That's it in our calculations. So that is the things that our beam slab will not going to have any collapse. Okay, the brittle failures will not happen. It will be stay there. It will have a ductility, meaning that look, the failure will happen, but it will not going to be sudden failures. Okay. Then crack controls. I think restrain moderated crack controls. I think if you just go back and do this one in the secondary directions, I think I can explain you in the secondary directions. Where was that? Now in the secondary directions, I'm not sure whether I done that one. You don't need to multiply this 75%. You just straight away come here in the secondary directions. You put 3.5, 2.5, sigma CP is 0, B is 1000, D is 150 times this one. So you don't need to multiply by 75. Okay, here in the secondary direction, because we are not working in primary directions. We are working in the secondary direction. Again, same assumption, Rosten slab, moderated control and so on. So only difference between the previous one and this one, we don't want to multiply 7. I think I'm not sure I done it or not at that time. But I think I think I calculated, but you can check it by yourself. But in here you don't need to take into account that 75% as we done before, right? You remember that? You remember that, right? 75%. So here everything same, just don't take into account this 75. 394, I think that was not good. So you just no need to take into account these 75%. And again you check. Let me do it for you, please. So here we have a 3.5, that's 0 times 1000 times 150 divided by 1000. You get 525. Sorry, this will not be correct. So you just make it this one to please make correction, 525 millimeter square per meter. And everywhere you need to provide this 525 spacing. So if you come back here in our Rio tables, 525. So everywhere I think you just need to change everything here. Look, this one is very quite high. As you can see in the secondary directions, you are shrinkage and control is significant. Like in the primary directions, you are providing only temperature and shrinkage control only 393, about 400, and you are increasing by 525 millimeters square per meter. This is quite significant. Is it? Am I doing correctly? Let me check. Shrinkage, temperature, moderate control. Again, they multiply by 0.75. Just give me a minute, please. I think we don't need to multiply maximum center to center. Yeah, but I think it will comes down to the center to center spacing. But I think you no need to multiply by the reinforcement in second direction and untransit. I think you no need to multiply by 75% here. I can't see in the standards. So just keep it 525, and from that one we can calculate the spacing. Where is the Rio tables? Yeah. We have 525. We don't have yeah, 525. Yep, here you go. You can provide the center to center distance of 200. So I think we have a 200 and 12 bar 565. So here in secondary directions you can provide N12 bar at the rate 200. Actual AST is 500. How much? 565. Sorry. Yep. 565 millimeters square per meter. So that is 565 millimeters square and N12 at the rate 200, and that is secondary direction. So everywhere in the secondary directions you put N12 at the rate 200. Now CR1, I think I can show you that CR1. I think you can calculate the V star using that same approach that we use in the one-way slabs. You remember that CR1? I think in the chapter 6. Here one CR1 transverse design shear. I think there is no any shear exterior corners. No, there is no any shear that we just going to talk about. No, the CR1 we just need to use it this close 1.15 FDLN over 2. That is for interior support where you have a significant shear. So look, we don't provide the reinforcement, shear reinforcement like a fitments, but we do check. So you calculate this V star, and you know this KV, BV, DV, FC dash. Okay, same thing that we discuss it like in the one-way slabs. If you go through it, I'm sure you will not be disappointed to have this one. So basically, your shear of the concrete would be adequate. That will take into account that V star. So you don't need too much worry about this V star. So, but you do checks. You do checks this one, and if you do these checks, I'm sure you will not be have any issue. So as you can see, you remember that we calculate this primary reinforcement N12 280 center to center distance, 280 center to center distance. I think we just change it to 250 center to center distance, or you can have 280 center to center distance as well. Then in the secondary directions, probably in the secondary directions we use 200, right? So yes, so in the secondary directions, if you are looking from these sides, this would be if you want 200, and that is also satisfy this value. So it's just a detailing that you can provide these bars, and you can provide these secondary bars. So I hope that makes sense. I think that is again, yeah, talking about this primary Rio at the bottom, secondary Rio 280 CTC. This secondary Rio here. I think this is secondary Rio. I put secondary Rio here. 200 everywhere, 280 secondary Rio here, and the bottom secondary Rio. So it's just distributing your secondary reinforcement in the directions. Now there was one more questions though, that you need to calculate this. You need to calculate this loading on the beam. You need to calculate this loading on the beam. Design reinforcement corner slab, determining the total floor load on beam AB and AC. So we need to calculate how much load coming on this AB, like a dead load, and how much load is coming on AC, right? So there is the calculations goes this way, that let's start with beam AB and close 6.10.3.4. Let me show you. Okay. There is a close 6.10.3.4. There is a load allocations. If you read this one, these figures will be helpful. That if you have a beam, then you have this beam will have this triangle. This beam will have a trapezoidal. This beam has a triangle. And this beam, the longer side of the beam will have a trapezoidal. Shorter side of the beam will have a triangle. That's how it distributes. Like shorter length will have a triangle distribution, and this slab has these directions. So in that case, we can calculate that. Do they mention anything? No, let's do it. Now total load is a tributary area times the times by this our Q star, that our 9.6 kilonewton per meter square. You remember that kilopascal, then you can get the kilonewtons. Now how do you get the tributary area? Because you remember that in our figures, in our questions. Let's keep this file here and then we open the questions from that other side. So remember that standards one, that shorter side of the beam will have a triangles, right? So for this beam AB, we need to find this area. We need to find this area because shorter side is a triangles, right? The shorter side is a triangle one. So if someone asks you to find this area, you know this is 5.5. You know this height that we're going to calculate from this 7500. I think that height I'm going to help you to calculate. So that height is 2.75. How it going to work it out? This will distribute like this: 2.75, 2 meters and 2.75 meters. It dimensions everywhere for that kind of a trapezoidal, because when you have a 45 degree and 45 degree here, I think here, if you just do the trigonometry, 45 degree here, 45 degree here, and you are in the positions to calculate this one, you can calculate this one. I think I done some trigonometry. I found that is 2.75, that is 2, and that is 2.75. If you do the basic maths, you are in the position. If you know this distance and if you know this is 45, you can calculate this ones, right? I hope you understand that if you know this is 45, this is half of these 5.5, then you are in the positions to calculate this distance, which is 2.75. So area of the triangles, 1/2 times base 2.75 times 2.75 height 3.8, and we have a two triangles, so you have 7.6 meters square. So tributary area 7.9.6 we calculated. Remember FD 1.2 G plus 1.5 Q. So that is done. Now total load. Now in the beam AC, where is the beam AC? Beam AC is here. Then you have this tributary area here that we can just find the trapezoidal. That is coming, by the way, from these standards. Okay. So in that case, we can have this trapezoidal. I calculate these 2.75 from these I think triangles. If you know somehow this distance, and then you are in the positions to calculate this 2.75 to 2.75. Now the area of the trapezoidal is A plus B over 2H. Your A is 2 meters. So by the way, this A is 2 meters. B is 7.5. That is your whole B. And H is 2.75. That's from here to here, 2.75. If you plug, then your get area is 13 meters square, and you have area of two trapezoidals, so that you have 26 meters square, and you again multiply, you get 250 kilonewtons load coming onto that beams. So I think that's in the nutshells. I think there was one more that you can do it yourself. This deflection of the, so there was a simplified calculations. If you remember that we have 3 different methods to check the serviceability. 3 different methods in the way that we have a simplify methods, we have these refined calculations, and we have deemed to conform. At the start we do the deemed. This is very conservative, deemed to conform. Okay, this is very conservative. Actual deflection should be calculated by simplify method. So if you follow this procedure in our beam examples, and then if you calculate the deflections, I think this is all gross, I crack, I effectives. We already gone through. If you calculate this total deflection 14.4, which is less than your limits, then the slab is adoptable. There is no any issue. It's just like a service liability checks.